And so what had happened was they were a day away from re-entry into the atmosphere. The mission was over. On the underside of the space shuttle, where the tiles are, which is super critical, an icicle 4 or 5 feet long had grown. And so the vent valve had malfunctioned, and so this icicle had probably been growing over the whole mission. So this again is a very serious situation. The first thing the space shuttle would do before re-entry is turn around backwards, fire its control rockets to slow itself down, and that would automatically start the re-entry phase because you've lost your velocity. And so they came to us and said, well, do you think you can maneuver your arm right underneath the space shuttle and get to within 1/8 of an inch of those thermal tiles? So we knew the reach was there. It was all about the control system. And so basically, if you touch one of those control tiles with your finger, with those thermal tiles with your finger, it will disintegrate. There is no strength to those tiles. They're just like ash that is sitting there. And so it was obviously very critical. So we did a simulation back in Toronto, demonstrated it could be done. And so the actual operational cycle was figured out, and we went in and got ourselves within 1/8 of an inch and just pushed the icicle off. So in itself, that was still a dangerous thing to do because we didn't know where the icicle was going to go. This is actually a cartoon out of a Toronto paper, which didn't impress NASA much, but it kind of illustrates the issue we were dealing with. So, having talked about a 6 degree of freedom system, if you remember the Columbia accident, the Columbia disintegrated on re-entry because the leading edge here had been damaged on launch, and they didn't know that. And so the spacecraft was basically grounded for 3 years. And NASA came to us and said, okay, what can we do to extend the arm to go underneath the space shuttle and inspect every tile, all along the underside, on the belly, on the nose, and so on. And so we had a number of spare parts in-house for a real flight arm, and basically we became the critical path to get back on orbit. And so I've forgotten the exact time. I think they gave us 11 months to produce this system and get it down for flight. And the program manager who did it sitting in the back there, and I think we delivered it 2 days early on Christmas Eve. And so ever since then, that's been the system of robotics. It's been used to inspect the space shuttle immediately they get on orbit and immediately prior to leaving orbit. The sad part is, in 2 days from now, it will do this for the very last time, and on Wednesday or Thursday, the space shuttle will land, and the whole program ends. So, but it's been a great piece of history, and we wouldn't have missed it for anything. So then we moved on to the International Space Station. So here is the space shuttle approaching the space station. So here we have a 6 degree of freedom robotic system. Here's what we did to build the robotics for the space station. So here we have 24 degrees of freedom. So we have a degree of freedom here which translates this whole thing along the space station. The space station is as big as a football field. So we can translate from one end to the other by driving this base along the system. The main robotic arm here, which most people call CANADARM-2, we refer to it as SSRMS, Space Station Remote Manipulator System. This has 7 degrees of freedom. So what is unique about this arm is this is an arm that can actually walk by itself. So what we mean by that is it has a shoulder on both ends and it has a wrist on both ends. And so what it can do is it's actually on this base here. It could let go at this end and find another fixture here, attach itself here, let go at this end, and inchworm its way along the whole space station. So that was one of the unique things about what when you hear CANADARM-2, that's what they're referring to. The video that Nurhan just showed you was a short burst of the assembly of the International Space Station. It took 60 flights of the space shuttle and Russian rockets to get all the hardware into space. And the combination of the CANADARM-1 and the CANADARM-2 on the base here took part in every one of those flights. And I think Canada was, well, we were the only company, I think, who had hardware on every flight and was a major part of the assembly of every flight. So the fundamental purposes of this system were twofold. When we set out to design it, the requirement was, firstly, you have to be able to robotically assemble the space station, including payloads as much as 200,000 or 300,000 pounds. And secondly, you have to be able to maintain the space station robotically. So there are about 300 items on the space station from countries all over the world that can interface with the Canadian robotics. And when the time comes, when and if there's a failure, we have to go out there and robotically change these things out without an astronaut going outside. Because even though the astronauts love doing EVA, it is a very expensive thing to do, and it's a relatively dangerous thing to do. So on the space station, we've largely, now the thing is completely assembled, we've removed a lot of the need for EVA. So the other piece of the space station hardware, which I showed you before, if you just stare at that for a minute and you start to get used to the weird ways it looks, you begin to realize it's pretty well a full human being. And so it has two arms, they're about 10 feet long. Those arms have 7 degrees of freedom. The CANADARM has 6 degrees of freedom, which is the same as your arm. So what this has is a wrist on both ends. And so this arm is obviously way bigger than your arm, but it's way more dexterous than your arm. And so then we have 2 feet. This is a foot, or it's actually an end effector. The purpose of this is so this device can locate itself anywhere on the space station and kind of bolt itself down. The other foot is for when the CANADARM-2 comes along and picks it up, and that puts it in the 24 degrees of freedom mode. There are 4 eyes on here. That's an eye, there's an eye there, there's an eye here. It turns up the waist. It can turn up its waist way more than you can. And so that's where it gets its dexterity. And this is the actual piece of equipment, I think, that made a quantum leap for Canada. We'd obviously done CANADARM on the space shuttle. We had done the big arm for space station, but this actually leapfrogged us ahead of the other countries. Japan had put an arm on the space station, and so this kind of leapfrogged Japan and got us back in the lead, which is the way we looked at it. So moving ahead to medical, this became the model for our first medical project. And so we got a call one day from a brain surgeon in Canada who said, "Seeing what you guys have been doing, I want one of these." And so we went to meet with him and said, "Well, what are you trying to do with it?" He said, "I want to perform microsurgery in an MRI machine. I want to perform stereotaxy in an MRI machine. And I want to be sitting outside of the operating room. And I want to have 3D vision at my workstation outside of the operating room." So we showed him this view graph. And so what we actually did to create his system, we cut this off here. We cut it off there, and we miniaturized this arm and this arm down to about 3 feet. So the miniaturization was not that difficult, but the problem was, how do you put a robotic arm inside an MRI machine without influencing the output of the MRI machine and having the MRI machine damage the arm.